If you have been using LAMMPS for molecular dynamic simulations, you know that the very first step is often to create an initial configuration. So in this video, I'm going to show you 5 ways to create an initial structure for LAMMPS, and I will cover both the cases of crystalline and non-crystalline configuration. So let's start with the first example. The first possibility here to create a new configuration is to create a lattice directly in the LAMMPS input file. So let's see an example here. So here, let's open this example. This is an example here for a silicon crystal. And the way you can define a crystalline structure, if it's a simple crystalline structure, very often the simplest way will be to define it directly in the LAMMPS input file. So for example, here you can define the type of lattice. In this case, it's going to be a diamond style lattice. But if you have a simple lattice like a cubic or a face-centered lattice or anything like that, so those are going to be supported by LAMMPS, then you can define the lattice parameter in angstrom, and then you can replicate this unit cell, decide how big your supercell is going to be by defining the region of the simulation box. Then you create the box, you create the atoms, and this is going to define a supercell where the unit cell is going to be replicated a certain number of times, and this is going to be your initial system. So after that, you can just proceed as usual. You can define your potential. In this case, we are going to use a Stilliger-Weber potential, which is a good potential to simulate silicon. Then you would proceed as usual, defining your neighbor list, defining the parameters of the molecular dynamic simulation, like the time step, the initial temperature, defining how often you want to output the thermodynamical properties or how often you want to dump the configuration. And then you can create your molecular dynamics. So in this case, it's a simulation in the NVT ensemble, just a short example with 1000 steps at 300 Kelvin. And after that, you can write the final configuration as a LAMMPS data file so that later on you can reuse this configuration as an initial starting point for a future simulation. So let's run this. So this is a simulation that is very quick to run. And so let's see what has been created. So if you see here, it has created a final configuration that can be used. So let's take a look at this configuration here. And we can take a look at it, for example, in your favorite visualization software. For example, Ovito is typically a one that is easy to use and easy to get started with. So let's load this in Ovito. So this is what it would look like. So here, as expected, it has created a supercell with a diamond silicon structure. And it is simulating that at 300K, so you have some slight vibration corresponding to the thermal vibration at room temperature that you expect for a system like silicon. So that's the first way, directly defining the lattice in LAMMPS, and that's a good way again if your system is very simple, maybe with a single type of atom or with a very clear and simple lattice structure. So now if your system is more complex and have a more complex structure, a more complex unit cell that would be more tedious to define in LAMMPS, a second option is to use a CIF file that you would have downloaded from a database of crystalline structure. So for example, here, what I got is a CIF file for an LSIM, which is the structure of a zeolite, so an aluminosilicate system. And so let's see if you want to use such a CIF file. Let's see how you can transform this into a LAMMPS data file that can be used as a starting point for a simulation. So here, the way you can do that, you have various ways, but a simple way is to use the Atomsk package. So in this case, this Atomsk is very good at converting atomic configuration from one format to another. And in this case, it's a very simple task, converting a CIF file into a LAMMPS data file. So Atomsk would be a very good and simple option in this case. So here, all you have to do is to run the Atomsk command, say that you want to convert the analsim CIF file, and say that you want to convert that into the LAMMPS format, which for Atomsk is known as LMP. And if you run this, it's going to directly convert this into a LAMMPS format data file. So it will have created that with an extension .lmp, which is the LAMMPS format extension that Atomsk is using. Let's take a look at this file here. So as you can see here, it looks just like a regular data file that you would be used to if you have been using LAMMPS already, where you define the number of atoms, the number of types of atoms, you define the lower and upper bound of your simulation box along X, Y, and Z. In this case, it's using a cubic box. Then you define the mass of the atoms, and then the position and the types of all the atoms, right? So the ID of the atom, the type of the atom, and then the position X, Y, Z of the atoms. And so then once you have this, you can, if you want, rename this file as analsim.dat, for example, which is more like the extension that we are typically used to when using LAMMPS. And then you can directly use this data file in your input file, and LAMMPS will be considering that as the initial configuration to get started with. So that's the second option, starting with a crystallographic structure that you have downloaded from a mineralogy database, for example, and converting that into a LAMMPS data file. So next option is if you want now to create a disordered structure that is not a crystal, then something that you can always do is to start from a crystal and then melt it to turn it into a liquid and then requench it pretty fast. And that will allow you to create a disordered structure, which is helpful if you want to simulate either a liquid or simulate a glass or simulate like another system like a polymer or something like that that does not follow a fully periodic crystalline structure that follows a lattice. So here, let's see an example of that. So for this, we are going to simulate a liquid water system. And so for this, we are going to use the approach of first creating a crystal water, so a system of ice water, where the system would be fully periodic initially. And then we are going to melt this system in LAMMPS and then requench it down to room temperature. And at the end, you will have an initial structure of liquid water that you can use as a starting point for a subsequent simulation. So let's see how to do that. So first, here I'm starting from a water CIF file. So this would be a file that, again, you can download from a crystalline database. So this would be a file that defines the crystalline structure of ice water. So the first step now is that we are going to convert this into a LAMMPS data file. So for this, again, we are going to use Atomsk. So I'm going to use this h2o.cif file. This time, if we only do that, this CIF file only comes with just a few water molecules. So if we want to simulate a bigger system, a larger system, we can define a supercell by replicating this system along the X, Y, and Z direction. And that's something that is, again, very easy to do with Atomsk. So all you have to do is to use the duplicate field here and then define the size of your supercell. So for example, here I'm going to replicate this initial unit cell 3 times along X, 3 times along Y, and 3 times along Z. And here in this case, if you want to use a force field that is going to use the charges of the atoms as part of to calculate the Coulombic interaction or to do some charge equilibration, then we need to also define the charges of the atoms. And so for this, I have a file here where I have defined the charges of all the atoms. So for example, we're going to use a charge of +1 for H and a charge of -2 for O, so the formal charge for hydrogen and oxygen. And then we can just put this as a text file here with this format. And then we can pass this to Atomsk so that it can use those charges when creating the LAMMPS data file. So let's do that. So we are going to, again, use this CIF file, duplicate the unit cell to create a 3 by 3 by 3 supercell. And then I'm going to define some additional properties to be used with by Atomsk, and I'm going to say to use this charge.txt file where I have defined the charge of oxygen and hydrogen, and then I am going to finish by telling Atomsk to eventually convert this configuration into the LAMMPS data format. So let's do that. Again, was pretty quick. So now it has created the H2O.LMP file. If we take a look, so this file contains almost 1,000 atoms with 2 atom types, hydrogen, oxygen. It has defined the simulation box, which in this case is triclinic. So you also need to define XY, XZ, and YZ. It has defined the masses of the atoms, and it has created the position XYZ of the atoms that constitute the water molecules. And this time, because I have provided the charge of the atoms, it's using the charge LAMMPS format, where this time you have the atom ID, the type of each atom, 1 for hydrogen, 2 for oxygen, and then the charge of the atom. So +1 for hydrogen, -2 for oxygen, and then the position X, Y, and Z of each atom individually. So then from this point, you can, so this is going to be still a crystalline ice structure at this point. So what you can do is to rename this file H2O.LMP into H2O.DAT so that we can use this as a starting point, as a data file for LAMMPS. Let's take a quick look at this file to confirm that everything looks good. So we're going to open this file here into Ovito and see what it looks like. So let me take the right file. And so if we look at this file in Ovito, so far what you have is this file here where you have a crystalline ice structure. We can define some bonds to better see the structure here by, for example, putting a cutoff of 1.2. And so here, so far what we have are some water molecules that are perfectly periodic, perfectly organized with an ice crystalline structure. So now, next step, now that we have this crystalline structure, what we want is to create a liquid water structure. And so the way we are going to do that is by heating up this system, completely melting the ice, mixing that at high temperature to mix the atoms and turning this into a disordered water system, and then requench this back to room temperature at 300 K, and then from this point save this configuration so that you can reuse this for subsequent simulation. So let's see how you can do that in LAMMPS. Again, that's going to be a very easy input file. You just define, in this case, the type of atoms that we are going to be working with, which in this case is charges. then in this case, we are just reading the LAMMPS data file that has been created by Atomsk. Then in this case, we are going to define a potential. So in this case, I'm using the ReactFF reactive potential to simulate water, which is a convenient potential to use because you don't have to define explicitly every OH bonds in the structure. It's just treating hydrogen and oxygen atoms individually and then dynamically defining the bonds on the fly. So it's a pretty computationally heavy force field, but it's pretty accurate and it's pretty convenient to use. So then in the context of ReactFF, it uses charge equilibration method to calculate the charges, the partial charges on each atom, and then the Coulombic interaction between the atoms. So we are going to set that up here. Then we define the neighbor list as usual, the parameters of the molecular dynamics simulation. With LAMMPS, and with ReactFF, we need to use a small time step when simulating water because the OH bonds are vibrating very fast. So here we are going to use a time step of 0.5 femtosecond. And then you define your output parameters. And then so what we are going to do is a 3-step molecular dynamics run where first step, we are going to do a simulation in the NVT ensemble. So in the canonical ensemble, where we are going to gradually increase the temperature from 300K to 500K. And we are going to do that here for 10 picoseconds. You can do that a little bit longer if you want to make sure that your system is fully equilibrated. Then we are going to mix this system at elevated temperature. So for water, you don't need to go at very high temperature. 500K is going to be enough to melt ice within 10 picoseconds. And in this case here, because we are in the NVT ensemble, so it's not going to turn into a gas, it's not going to explode into a giant box. We are keeping the volume of the simulation box fixed. So it's going to keep the same density as the initial structure. And then at the end, the last thing we're going to do is to do another simulation of 10 picoseconds where we are going to now gradually decrease the temperature from 500K to 300K, so back to room temperature. And then at the end, we are going to save the final configuration as a data file, and then you would be able to use this final configuration as a starting point for a new simulation. So here this simulation would be a little bit long to do, so I'm going to skip it and just show you what the final result looks like. I'm going to open this file in Ovito. And so this is what it looks like. So now you have a liquid water structure where you still have the individual water molecules that have the geometry that you expect, with the 1 angstrom bond between the oxygen and the hydrogen and the right angle. But now the water molecules are not forming a crystal anymore. They are forming just a liquid water system. And again, this is because now your system has been heated and cooled, so it has lost the memory of the initial structure of the crystalline ice water. And now you have a liquid system that is disordered, that now you can use as a starting point for a new simulation, where now maybe you can add some extra ions within this water if this is what you want to do, and use this for subsequent simulations. Okay, so that was the third option, which you can use when you want to create a disordered system, a system that is non-periodic, non-crystalline, which is simply to start with a crystal, heat the system, mix it at elevated temperature, and then cool it down to the temperature at which you want to simulate your system. So now the drawback of this is two things. First, you need to have an initial crystalline structure with the right stoichiometry, with the right composition. So if you want to simulate a system that has a complex composition for which there is no crystal that has exactly this composition, then you would not be able to do that. And the second drawback here is that here we are keeping the geometry of the initial ice structure. So here you would end up with still a triclinic geometry for your box, which in this case is not really needed anymore, because now since you are simulating a liquid crystalline structure, it would be more convenient to simulate this in a cubic box, because you don't have to fulfill the geometry of the initial crystal anymore. So it would be more convenient to have this liquid water directly in a cubic box. And so if you want to do that, and if you want to work now with any stoichiometry, the fourth option will be to directly create a disordered structure from scratch without starting from a crystal and without having to first heating the system and then mixing it at elevated temperature. So there is various tools that you can use to do that. The idea of those tools is that they are going to just create a box, a simulation box, and then they are going to pack randomly some molecules in this box. Randomly, but not perfectly randomly. They are going to randomly fill the box with those molecules, but always ensuring that those molecules don't overlap with each other, which is important because if you start, for example, if you want to simulate water and you just put randomly in the box some oxygen and hydrogen water, then first you would not have the right OH bonds. The system would not be realistic, but also you would have a high risk to have some atoms that are actually very close from each other. For example, an oxygen that would be very close to another oxygen, and in that case that could cause your system to be unstable, to explode when you put that in LAMMPS. So those package like the one that we are going to be using here, which is Packmol, have been optimized so that you can they are able to pack a lot of molecules in a small space, and to do this in an efficient way so that there is no overlap between the atoms, but there is also not so much empty space between the atoms. So for this, let's look at the example of Packmol, which is a pretty popular package in order to create initial disordered structure. So let's see what you need to use Packmol. So here what we are going to use is some initial PDB file. So those PDB files, they are going to define the geometries of the molecules that we want to pack into our simulation box. So let's take a look at, for example, one of those. So we can look at the H2O PDB file. So this is a file that defines here the structure of a water molecule. It defines which atom the molecule is made of. It defines the position of the atoms with respect to each other in a molecule, and then it defines how those atoms are connected with each other to form some bonds. So here we are going to create a system that contains some hydrated carbons atoms within a water solution. So for this we need two types of molecules. One is H2O, water molecule, so we have the right PDB file to do that. And the next one is to have a H2CO3 molecule, so a hydrated carbon molecule. So we are going to use this structure here where you have a CO2, a hydrated CO2 species, where you have a carbon surrounded by free oxygen and attached to two hydrogens for charge neutrality. And again, so you have this file here, this PDB file that defines the structure of this CO3H2 molecule. And then all we need to do is to set up a few options within a Packmol input file to define how many molecules do we want to pack and in which space, and how do we want to pack them. So for this you need to define a Packmol input file, which typically has the extension INP. So let's look at what this file looks like. So here you can write some comments like this. So here we're going to create a structure that will be disordered, that will contain some hydrated CO2 species. within a water environment. The first thing that you will need to do is to define the tolerance. So the tolerance is the minimum distance between two molecules. So what Packmol is going to do is to randomly place those molecules of CO2, hydrated CO2 and H2O into a cubic simulation box, but it's always going to ensure that two molecules cannot be closer than 2 angstrom away from each other, so that there is no overlap, so that when you will put your system into LAMMPS, it won't explode because you have two water molecules that would be too close to each other, for example. So then you can define the type of file that Packmol is going to create as an output. So Packmol cannot create directly a data file, a LAMMPS data file, but what you can do is just to create as an output a PDB file, and then we will use Atomsk to convert this PDB file into a LAMMPS data file, which again will be very easy to do with Atomsk. So then you can define here the name of the output file with the atomic structure that will be created by Packmol. Then the next step, which is again very important, is that Packmol by default doesn't take into account periodic boundary conditions. And the problem with that is that when Packmol is going to place those molecules randomly into the simulation box, since Packmol is not aware of periodic boundary condition, if you have one molecule that is at the very top of the simulation box and then another molecule that is at the very bottom of the simulation box, then to the eye of Packmol, they are going to be very far from each other. But then when you will use this as an input for LAMMPS, LAMMPS will consider that those two molecules are extremely close to each other because they are actually seeing each other through the periodic boundary condition. The top of the simulation box will be very close to the bottom of the simulation box. So that's something that you can avoid by adding an additional margin of safety. So here what you can do with this add box sides is to tell Packmol to create an initial box where it's going to try to fill as many water molecules and hydrated CO2 species in this box. But then on top of that, it's going to add an extra 1 angstrom of empty space around the simulation box. And the goal of this is to avoid having any spurious pair of atoms that would be very close to each other because of the periodic boundary condition. So by adding this extra margin of safety, this extra empty space around the simulation configuration that is going to be created by Packmol, then you prevent completely the risk of having some molecules that are becoming close to each other through the periodic boundary conditions of the simulation. So this is going to create quite a bit of empty space around the simulation box, which is not going to be realistic. But as soon as you will place this into LAMMPS, and as soon as you will start, for example, an NVT simulation, the water molecules and the hydrated CO2 molecules are going to just fill this empty space very quickly. And just after a few femtoseconds, the system will have occupied the full space available to the system, to the atoms. And at this point, you will be able to get a realistic structure very quickly. It will have forgotten the memory of this initial empty space that was created by Packmol. So again, this is an important step here, and it's just a temporary empty space around the simulation to avoid unrealistic overlaps between the atoms, and it's going to be very quickly filled with atoms as soon as you start an NVT simulation. So next, once you have this, the next step is to say that we are going to use some molecules that are defined in the PDB file. So here we can specify the name of the two PDB file, the two types of molecules that Packmol is going to try inserting into the simulation box. then we need to define how many molecules of each types do we want to insert into the box. So we are going to, for example, in this case here, have 100 hydrated CO2 species in the box, and we are going to insert 400 H2O molecules, 400 water molecules, and then you can define the extent of the box, the extent of the space where Packmol is going to try to fill those molecules. So here in this case, we are defining a cubic box that is 30 angstrom long on the X, Y, and Z axis. And so what Packmol is going to do is to take this simulation box, this cubic simulation box, and try filling it with 100 H2CO3 molecules and 400 molecules of water. And it's going to do that by packing those molecules as efficiently as possible, but while always ensuring that there is at least 2 angstrom of distance between 2 neighboring water molecules. So once you have defined this Packmol input file, all you have to do is to run Packmol. So we are going to run Packmol and say that we are going to use as input this CO2-H2O.inp file, and then Packmol is going to do that, and in just a few milliseconds here, it's able to create a PDB file of the liquid configuration. Let's see what this file looks like here. So you have here the structure that you would expect for such a file with the types of all the atoms. So here we have some carbon, some oxygen, some hydrogen, and we have the position of the atoms. Let's see what this file looks like here. So again, we can open this file in Ovito. Actually, let's just directly convert this file into a LAMMPS format. So for this, again, you can use the Atomsk package, say that you want to convert this liquid.pdb file and convert this into a LAMMPS data format. And Atomsk will do that very easily. And so now you have a liquid.lmp file. We can rename this into liquid.dat to have the extension that we typically use for LAMMPS data file. Now let's look at what this file looks like here. So let's open this in Ovito. And let's see what it looks like. And so this is what the system looks like. So here, in this case, you have a cubic box. So this is one advantage of this approach, is that not only you have created the disordered structure from scratch, you don't need to have a crystal, a preliminary crystal with the right composition or the right stoichiometry. You can directly define the stoichiometry that you want in Packmol. And you can directly simulate a cubic box, which is another advantage to have a system that is easier to use. And so if you look in more detail here, so you would have your water molecules here, and you would have the hydrated CO3, the hydrated CO2 species. So let's define. We can define some bonds here again to better see what the structure looks like. So you have here those hydrated CO2 species, so the CO3H2, and so it has randomly packed all of those molecules together. And so what you get at the end is this kind of aqueous system where you have those hydrated CO2 species that are in water condition. So you can see here that the simulation box indeed has some empty space on the side here. This is again what we had defined in in Packmol to avoid having some spurious interaction between water molecules that would otherwise run the risk of being very close to each other through the periodic boundary condition. And so by adding this empty space, we remove that risk. And as soon as we are going to simulate this in LAMMPS, the molecules are going to just fill the space, and molecules are going to start interacting with each other through periodic boundary condition, and you will end up with a bulk liquid. And so after you simulate this for a few picoseconds, you will have an equilibrated liquid structure that you can save and use as a starting point for a subsequent simulation. So this was the fourth approach, which again is consists in this case in starting with some initial geometry for your molecules, and then using a tool like Packmol to pack those molecules into a cubic box and directly generate a cubic structure, a cubic box with a disordered structure that you can use as a starting point for a LAMMPS simulation. So now if this still doesn't meet what you need for your system, if, for example, if you have a complex polymer system where you need to define how the molecules are attached with each other in a way that is not perfectly periodic, that is not a perfect crystal, but that is still have some level of order, then it's possible that you will have to go to the option 5. Option 5 is just to write your own script. The data file that is used as input for LAMMPS is just a text file with a pretty clear format. So if you want to create your own text file, your own data file with a customized requirement in the way the atoms should be organized, then what you will need to do is to write your own script. So, for example, you can write a Python script that's going to generate the position of the atoms and then generate a text file that will have the right format to be considered a valid data file by LAMMPS. So what you will need to do for this is to define, for example, a space, which will be the space of the simulation box where the atoms will be placed. Then you will need most likely to define what is the minimum distance between the atoms or the minimum distance between the molecules, just like what we did in Packmol. And then you will need to write a script that's going to start, for example, placing randomly the molecules or the atoms inside the simulation box. And the way you would do that is, for example, by generating some random numbers, which are going to be giving you the position of the atoms within the box. So, for example, if you have a box that is that has a size of 30 by 30 by 30 angstrom, you can simulate a random number between 0 and 1, then take this number and multiply it by 30. So that's going to be that's going to give you a random number between 0 and 30, and that's going to give you a random position for x. Then you can do the same for y and z. And then what you can do then is to check, once you have this random position being generated, you can check if when you place this atom or this molecule into the simulation box, is it close to another molecule or to another atom or not? So if it's far away from all the other surrounding molecules, then you can accept this insertion and start trying to insert now a new molecule or a new atom. Or if it happens that it's too close to another molecule, if it's within a certain distance, a certain threshold from other atoms or other molecules, then you need to try again. You need to start generating a new series of random number and try putting the molecule at another position. And then you need to iterate until you have placed all the atoms, all the molecules within your box. And once you have reached the density that you want. Something that can make this easier, since it's in practice, it's not always easy to pack a high number of molecules to reach a high density liquid, for example. There is a high risk to just running out of space completely if your packing algorithm is not very efficient or not as efficient as the one of Packmol, for example. One trick that you can use is to start by creating a very large system with a very low density. So you can try, for example, to place 100 water molecule into a very large system, for example, a large simulation box of 100 by 100 by 100 angstrom. So you are going to start with a very dilute system where it's going to be very easy to place all your molecules without having them overlapping with each other. At this point, the system will be unrealistic. It's going to be very low density, where the molecules would be very far away from each other. But once you have generated the structure, what you can do is to use it as an input, as an initial the configuration, place that in LAMMPS and start running a simulation in the NPT ensemble, for example, with a pressure of, let's say, 1 gigapascal. And this pressure is going to force compressing the system. It's going to force the molecules or the atoms to come close to each other. And then after that, you can go back to doing a subsequent simulation at 1 atmosphere or just zero pressure altogether. And at this point, you will end up with a dense system that would have the equilibrium density that the system wants to have at this temperature. And from this point, you will have a liquid configuration that you can use as a starting point for a new simulation. So there you have it. Those are 5 different ways to generate either a crystalline or a non-crystalline configuration for that you can use as a starting point, as an initial configuration for LAMMPS. So now if you want to learn more about LAMMPS, so if you are getting started with LAMMPS, if you want to learn more, if you want to learn how to write the full input file, how to set up the potential, how to run the molecular dynamics, how to pick the right ensemble, I have a 2-hour full tutorial that will take you step by step on how to quickly get started with LAMMPS. So if you're interested in that, make sure to watch this video.